A tornado is not just a strong windstorm. It is a concentrated, rapidly rotating column of air that connects the bottom of a thunderstorm to the ground. That full connection matters, because the danger is not only in the cloud above but in the energy transferred all the way down to surface level where people, homes, roads, and infrastructure exist. Many people picture tornadoes as giant black funnels, but the funnel itself is only part of what you are seeing. The visible cone is usually condensation, formed when pressure drops and moisture in the air condenses. Around the base, dirt and debris can be pulled into rotation, creating a wider and sometimes darker footprint than the funnel alone. This is one reason tornadoes can appear different in shape and color from one event to another. Some are thin ropes, some are wide wedges, and some are partly hidden by rain. The atmosphere does not produce a single textbook version. It produces rotating systems with different structures, but the same core principle: intense spin plus ground contact. Most tornadoes are on the weaker end of the spectrum compared with the rare monsters that dominate headlines. Typical tornadoes may have winds below about 180 km per hour, widths around tens of meters, and tracks that last only a short distance before dissipating. Even these can still cause serious local damage, especially when buildings are poorly anchored or when debris becomes airborne. At the other extreme, the strongest tornadoes can exceed 480 km per hour, stretch across several kilometers in width, and stay on the ground for very long paths. The difference between a brief weak tornado and a long-track violent one is not random luck alone. It comes from storm organization, available moisture, instability in the atmosphere, wind shear, and how long the storm's rotating updraft can maintain structure. Understanding that range helps explain why public warnings can sound urgent even when not every storm becomes historic. Tornado risk is about probability and potential impact, not certainty. You prepare for what could happen in minutes, because by the time certainty arrives, damage may already be underway. To understand how tornadoes form, begin with thunderstorm architecture. A cumulonimbus cloud can become a massive vertical engine where warm, moist air rises rapidly and cooler air sinks elsewhere. If winds change speed or direction with height, the atmosphere develops horizontal spin, like invisible rolling tubes of air. Strong updrafts can tilt that horizontal rotation upright, creating a rotating updraft called a mesocyclone in supercell storms. Once rotation is vertical and concentrated, pressure can drop near the center, accelerating inflow and tightening spin. Think of a skater pulling arms inward to rotate faster. If the process intensifies enough, a tornado can descend from the cloud base or develop upward from near-surface rotation and meet the lowering circulation. The exact sequence varies, but the key ingredients remain organized lift, rotation, and sustained storm dynamics. Tornado formation is often rapid from a human perspective, but meteorologically it is the end point of multiple interacting processes that have been building through the life cycle of the storm. Visibility can fool people during tornado events. A tornado is often visible as a condensation funnel, but not always. In some cases, the rotation reaches the ground before a full funnel appears, meaning you can have a dangerous tornado partly hidden in rain or darkness. In other cases, the most visible element is debris at ground level rather than the funnel shape in the sky. This is especially true in high precipitation storms where heavy rain wraps around the circulation. That wrapped rain can obscure the tornado until it is very close. Color is also not a reliable signal of intensity. A dark tornado may simply be carrying more debris or set against brighter background clouds, while a pale rope tornado can still be damaging. Relying only on sight is risky, particularly at night when contrast is poor and road noise masks approaching wind. This is why warning systems, radar interpretation, and local alert methods are critical. Tornado safety begins with accepting that the atmosphere does not always present danger in a dramatic, obvious way. Not all tornadoes share the same internal structure. A multiple vortex tornado contains smaller subvortices rotating around a common center. These subvortices can create pockets of extreme damage right next to less severe damage, which is why post-storm surveys sometimes show strange patterns where one house is heavily destroyed and another nearby is less affected. The parent circulation is already intense, but localized wind peaks and subvortices can be even stronger. Then there are landspouts, which usually form differently from classic supercell tornadoes. Landspouts are often associated with stretching of pre-existing low-level rotation under growing cumulus towers, without a deep mesocyclone aloft. They can still be hazardous, but they are often narrower and shorter-lived. Waterspouts add another category, typically forming over water and frequently in non-supercell environments, though classification can be debated depending on structure and parent storm. The practical takeaway is simple. Tornado-like hazards emerge from more than one pathway, so forecasters and the public need flexible pattern recognition instead of a one-model mindset. Geography matters because tornadoes depend on atmospheric ingredients meeting in the same place at the same time. The United States reports more tornadoes than any other country, especially across central and southeastern regions often called Tornado Alley, though dangerous activity extends beyond that label. One reason is the frequent collision of warm moist air from the Gulf, cooler dry air from higher terrain and continental interiors, and strong upper-level winds that enhance shear. This setup can repeatedly generate severe thunderstorms with rotating potential. But tornadoes are not a US-only phenomenon. They also occur in parts of Europe, South Africa, Bangladesh and eastern India, Australia, New Zealand, Japan, the Philippines, and sections of South America. What changes by region is frequency, seasonal timing, terrain influence, building resilience, and warning infrastructure. So while maps highlight hotspots, preparedness should not be confined to famous corridors. If your region can produce severe convection and directional wind shear, tornado risk exists, even if major outbreaks are less common than in North America. Modern tornado detection relies heavily on pulse Doppler radar, which allows meteorologists to analyze not only where precipitation is located but how air and particles are moving relative to the radar site. Reflectivity data can reveal storm structure, including curved appendages like hook echoes that often indicate rotating supercell organization. Velocity data can show inbound and outbound winds adjacent to each other, a signature of rotation. When that rotational signal strengthens and tightens at low levels, forecasters become increasingly concerned about tornado development. Another key indicator is a debris ball, where radar detects non-meteorological material lofted by a tornado, suggesting damage may already be occurring. Radar interpretation is not magic certainty. It is probabilistic and time-sensitive, and beam height increases with distance, which can limit low-level detail far from the radar. Still, combined with satellite, environmental analysis, and spotter reports, Doppler systems have transformed warning capability. The goal is lead time, enough minutes for people to move from normal activity into immediate shelter action. Human observation remains crucial even in a radar age. Storm spotters, trained volunteers, emergency managers, and local law enforcement provide ground truth that instruments alone cannot always deliver in real time. A radar signature might suggest rotation, but direct reports can confirm whether a funnel is visible, whether debris is airborne, and which communities are being affected first. This matters for warning updates, path projections, and emergency response routing. Spotter networks also help communicate nuances, such as a storm transitioning from hail-dominant behavior to tornadic behavior, or a rain-wrapped circulation crossing a highway where visibility is minimal. In fast-moving outbreaks, these reports can reduce uncertainty and improve decision speed for weather offices. Public trust is also reinforced when official warnings match what communities are seeing and sharing. Technology and people work best together. Radar gives broad surveillance, while observers provide local verification. In a hazard where minutes define outcomes, that integration can be the difference between a late reaction and a life-saving early move. The phrase tornado warning is often misunderstood as a distant possibility, when in fact it means dangerous rotation is detected or imminent for a specific area. Timing during severe weather is compressed. A storm can evolve quickly, and road-based escape attempts are frequently more dangerous than sheltering in place, especially in traffic, poor visibility, or nighttime conditions. The safest strategy begins before storms arrive. Know your shelter location, keep multiple alert channels active, and understand that mobile alerts, sirens, and broadcast updates serve different roles. Sirens are mainly outdoor alerts and may not be heard indoors clearly. Phone batteries can fail. Internet can drop. Redundancy is not paranoia, it is practical risk management. For homes without basements, the priority is an interior, windowless lowest-level room, as many walls between you and outside debris as possible. Helmets, sturdy shoes, and quick-access essentials can reduce injury after impact. Preparedness is less about fear and more about reducing decision friction when stress is highest and seconds matter most. Tornadoes also carry long after effects that are easy to underestimate when coverage focuses only on touchdown footage. Infrastructure damage can disrupt power, communications, water systems, and road access, delaying medical care and complicating family reunification. Economic recovery varies widely based on insurance coverage, local resources, and construction standards. Psychologically, communities can experience lasting stress from repeated severe weather seasons, especially where warnings are frequent and memories of prior losses remain vivid. That is why resilience is broader than storm chasing or dramatic video. It includes better building practices, accessible shelters, stronger local warning culture, and public education that translates atmospheric science into simple, repeatable actions. Tornadoes are violent, but they are not beyond understanding. The more clearly people grasp what tornadoes are, how they form, how they hide, and how warnings are issued, the more likely they are to respond early instead of hesitating. In tornado safety, clarity saves time, and time saves lives. If you found this helpful, please like this video and subscribe for more explainers.